Hello everyone. In this tutorial, we will discuss a quick sort algorithm, which is, as the name suggests, one of the sorting algorithms, which is one of the fastest, and which lies under divide and conquer algorithms category. So if you remember, if you have already watched the merge sort tutorial, we have already discussed divide and conquer algorithms. But for those who have not watched that video yet, or for those who doesn't know divide and conquer algorithms, what they are, it's like using recursive functions. We divide the problem into some smaller ones until we reach some small, let's say, segment or sub problem, which can be like solved very easily without needing to any computation, or we reach to some point where we should stop calculating and going further and should return. Okay, so quicksort is one of the divide and conquer algorithms, and in which in quicksort we will have two subtasks to perform a quicksort on a given array. One is partition, the other one is sort. Sort is the simplest recursive function, which we will do later. We will write the code for that directly, but partition is something that we should discuss a little bit deeper and try to understand well before switching to the coding part. So let's get started. Okay, here I took some array here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. So 9 elements array. We have 0 as the low index and high as the 8 as the last high index. Okay. So for partitioning, what I do, I take the pivot. Okay, and in my case, I take the middle one, but there are several other options as well. For instance, let me get back to here. Okay, it's the quick sort on Wikipedia, so you can also read this resource as well. Here there is two different schemes for the partition. One is the Lomuto, the other one is the Huare. The one that I will implement here is this one, the second one, but also for the previous one as well, we have several options. We can take the pivot as the first element of the array. For instance, in the first algorithm here, I can take this one as the pivot, or I can take this one as the pivot, making it two different versions. Or in my case, I'm implementing this one, and we have the pseudocode as well here. And here we will take the middle element as the pivot. Okay, so let's erase the link. Okay, so once we choose a pivot here, what we do, the main idea behind this algorithm, the partitioning algorithm, is that we take the lowest element here, which lies in the low index, and then we check it with this one, okay, with the high. And then we see that this pivot, which is in our case 8, right, according to this pivot, 10 should be right side of this 8 and this pivot, and 1 should be left side of 10. So that's why what I will do, I will basically swap these two. Okay, swap 10 and 1, which is the array of low index and array of high index. Okay, so after I swap these two, I will have something like this. So the first element of the array becomes 1, the last element of the array becomes 10, and then I update the low index and high index. And the reason for that is because I want to locate the other elements as well, which according to 8 are not in their correct position. All right, not the position, exact position, but the side, let's say. So according to this 8, we are trying to find what lies in the left should be less than 8, right? Less than pivot. So what lies in the right side of the pivot should be greater or equal to the pivot, right? So that's why I incremented low by 1 and I decremented high by 1. Okay, so first of all, let's stick with low. So when low is less than pivot, so that means 5 can still stay there because 5 is less than the pivot. This is the right side, the correct side of for 5. Okay, what about next? The next is I increment low by 1 because 5 was in its correct side, and 6, I check 6. So 6 compared to 8 is in its correct side as well. So that's why I will increment low 1 more time. And then let's check this one, because as you can see, 12 is greater than 8. So 12 is going to be swapped by something. Okay, so it's not in its correct position, correct side. So let's talk about high a little bit. So 5 compared to 8, which is pivot, right? 5 compared to pivot is less, right? So that should be somewhere to the left of pivot. So that's why this is also subject to change. So what I found here, 12 and 5 should be swapped, right? So after I swap these two, I will have 5 and 12. Okay. Now let's look at this. Low now indicates to the element 8, and high indicates to the element 7, right? So low 8 compared to 8, which is not less than pivot, right? So that's why we will mark it as to swap, okay, later. What about this one? 7 is less than 8. So this is supposed to be somewhere to the left of 8, right? So this one also going to be swapped. So when we swap 8 and 7, we will have something like this. Okay. Now what about next? So as we already saw, low should be incremented, right? So low is going to be +1, which is here. Now 0 is less than 8, right? 8 is the pivot. It's not this 8, it's pivot, right? Our pivot. So when low is less than pivot, it means low should be incremented 1 more, right? As you can see, it's yellow. The background is yellow, so low is pointing to this one. Now, what about high? High was in the like pointing to this element, which is not greater than 8, right? So that means we will get back to this one. So as you can see here, 0. Okay, so when we achieve this kind of situation, this is kind of tricky here. Before, for instance, here we use the swap when we find some kind of pairs which are not in their correct sides, all right, and then we swap them, right? But there is another like tricky condition here, is that low, okay, should be less than high. Oops. Okay, to be able to perform this swap operation. So in our case here, high is already less than low, so that's why it's not going to be possible to, not possible, but it's not right to swap these two elements. So that's why we will stop these steps here. You see, it's the last step, and I will not swap here. And what I will do, I will take the high, and from now on, I will treat it as the partition index. So partition index means that for the other steps, later on we will see, this partition index will perform some kind of splitter role. And this, let me show you this. Once I obtain the partition index means that the 8, okay, what was the previous pivot, right, is in its correct position. It's not about sides anymore. It's in its correct position. Means that everything which is greater than 8 is to the right side of 8, and everything which is smaller than 8 is to the left of 8. Okay, so once we have this kind of logical separation in our array, what we can do, we can perform the same operation that we have been doing for the left subarray plus the partition index, because each time we will decrement. So since this one was the pivot, this will be our let's say the partition index will be considered as the left subarray in the future, in the further operations. And then we will also do the same operation with the right subarrays. Okay, so I will not talk about that one in the slides, because we will write code for this kind of performing the same operations over and over, which is recursion, as you already know. But partition operation or algorithm was like this. First, we will pick the pivot, and then we will check if any element on the left is greater than the pivot. That means it should be somewhere to the right. And also similarly, if we have something in the right which is less than pivot, and that means should be to the left of the pivot. In that case, we should swap those until we have this condition. Okay, until we have this condition. Okay, so this is about partition. Now let's try to code this partition function, and then we will talk about sort as well. Okay, so let's come to here. So again, for those who already watched the video about merge sort, they know what print range is. But for those who did not, let me first show you the code segments that are already here, that are already defined. So Here I have print a range function, which takes an array, integer array as an input parameter, and two indexes, left index and right index. So the left index is for, it's like you have an array from what index to what index you want to print your array. Okay, this is basically printing your array. And we also have a swap function that's already defined. It's just basically I will send two integers, it will swap these integers, and that's it. Okay, so the next one that I would like to do, which we already discussed, is partition, right? So let me put it here. So partition takes one integer array as input parameter, and again left index and right index. Why left index and right index? Because as you remember, we will perform the same operation with some smaller array, with then some smaller array, then some smaller array, okay, and then to this one, so on and so forth. So each time you will keep on calling the same function, but this time for different range. That's why we will send these two arguments. Okay, here they are parameters, but when we send we are talking about arguments then. Okay, so first of all, let me do this. We have partition. Okay, so I have already marked the tasks that we are supposed to do. First of all, we have to initialize low and high indices. If we get back to this, okay, here as you can see, low index should start from the previous, from the beginning of the array, and the high index should start from the ending of the array. But if we do this, it will be slightly different than this. This pseudocode, because they start somewhere like this. When they start low, they start from the low index starts from. So when they start in the pseudocode, as you saw, they start low from the -1, and they start high from something which is outside of the boundary, both of them. Why? Because you will see later, we use do while repetition. First we increment or decrement, and then compare. So that's why here, if we take it as -1, as soon as we start, we will increment it by 1, so making it the first element of the array. And similarly here, which is in our case it was 9, I guess. As soon as we start, it will be decremented, so high will be starting from 8. Okay, so that's why I will do this similar stuff in order not to confuse you much. But of course, keep in mind that you can start from this, and then there is another condition I will show you later, which will be slightly different. So anyways, let's start. So int low starts from left index -1, and high starts from right index +1. Okay, so what else we need? We need the pivot as well. So the pivot is the element which lies at the middle of our array. So left index plus right index divided by 2. Okay, so once we have the pivot, now we should start. We can start partition. So in partitioning, what we have, let's stick with the only one step here. So what I do is that I check if this element. So it was -1. So I will increment until the time this element is somewhere. This element is somewhere. Is supposed to be somewhere to the right of the pivot. So that's why I will have while array of since we said that we should first increment and then compare, so it will be do low plus while array of low is not is in the correct size. So array of low is less than pivot. Okay, so this is the first one. So first we start trying to position low in somewhere that is supposed to be swapped, all right, which is not in their correct side. What about the next one? The next one is this. Again, do this time for the high. So high should be decremented while array of high is greater than the pivot. Because if it is not greater than the pivot, that means it's not in its correct position. Okay. And the next thing is that we have to perform the swap operation. Let me check. Where is that? Okay, we have to perform the swap operation if this is not the condition that we're facing. So if I will say low is less than high, what we are going to do is swap. So when we swap, as you remember, we send the addresses of those integers. So here I have array plus low as the first integer and array plus high as the second integer. So since array is the pointer plus some integer, it will give us another address. Okay, so if this is the thing here, we will swap. Yes. Now let's try to test this particular function. It's not completed yet, but let's try to see, because this will perform only one step on the array, and let's prove that it's performed it well. So now I will get back to main. I will call this partition function, sending my array, where the name of which is the vector, 0 as the left index and size -1 as the right index, because if you have size number of elements, the last index is size -1. So this is partition. After doing the first step of partition, let's print our vector. Let's print our array. So quick sort. Okay, now let's see. So after performing one partition operation, only one step of partition operation, as you can see, we have, it was 10 and 1 as the first and last elements accordingly, but here we have 1 as the first element and 10 as the last element. So that means the first step of partition is over. We successfully did this partition. You see here, it's supposed to be 1 and 10, right? So let's see what should be done in the second step. So tuck, 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 and 12 and 5 should be swapped, right? So let's see. If I want to perform the same operation again, I will copy this and paste it. Later on, we will put it in the repetition, but just to check if the second one goes right or not. So this is something that I will fix. So step 1, this is step 2. Let's see if it performs well or not. Okay, so 1, 5, you see 5 comes here and 12 goes there. 5 comes here and 12 goes there. So the first step and the second step, these are okay for now, for the moment. But what are we going to do now is we have to, as you saw, we have to put it in the repetition. Why in the repetition? Because right now we know that, okay, we have more or less 4 steps, but if we have larger array, or if we have a different structure of the ordering is the different, in that case, it would be even more steps or less steps. So that's why we cannot say how many number of exact steps will be done in one partition. So that's why one partition operation, let's say. So that's why what I will do, I will put it in the repetition. So the repetition is this. I will say, I will create a repetition, which is a, like simply forever, a infinite. Okay. And this is the repetition that will go over and over until some condition is met. And that condition was, if you remember, this. Okay, so here I have checked that condition, but I will slightly change it a little bit. So here I have, I will say if high is greater than or equal to low, I will say break out the repetition here. Otherwise, so if it didn't break, I will do swap operation. Okay, this is basically the same as the previous one, but since I have the repetition, I just changed the structure a little bit. So here, what this will do, it will start from the left index and start from the right index as high, and it will go forward, go backwards from beginning and ending until it finds the pair of values which should be swapped, or it finds that this condition is satisfied, is met, so it will break out the repetition. Once it breaks out the repetition, we have to send back, as you can see, one integer, which is the partition here, which is the partition index. Okay, so partition index should be returned, and in our case, what's the partition index? It is the current value of high. All right, so once we break out the repetition, we should return the value of high index. So we have two options: either we break here and return somewhere outside the while, or directly return high here, and this return will perform also as the break statement, because like, since return statement returns like breaks and like stops and returns from the function, it will like intuitively it will just stop the repetition as well. So this swap operation in the last pair will not be performed. All right, so I think that's it. Let's do this. Okay, let's try to call again. So it's supposed to perform all four steps by itself. So 10, no, let me see. Sorry, I didn't change the condition. If high is less than or equal to low, in that case, return high. Okay, so 1, 5, 6, 5, 7, 0, and 8, 12, 10. Let's compare it with this 1, 5, 6, 5, 7, 0, and 8, 12, and 10. So this one, we saw that this one is in its correct position, and everything to the right is supposed to be right, but no one guarantees that this side is sorted. So that's why we will take this partition index, this one, and we will call the partition again for left side and the right side. Okay, so let's do that. Since we are done with the partition so far, I will hide this implementation here, and I will get back to quicksort. So quicksort is taking the same amount and same amount of and the same input parameters, one integer array and two indexes, indicating the first like to the left index and to the right index. Okay, so since it's going to be a recursive function, you can say that it's recursive because it will do the same for this, and then the half of this, and then the right half of this, and so on. It's going to be a recursive function. Since it's a recursive function, we will first decide on the base case. The base case for this quicksort is that, you might guess, so the base case is that whenever left index steps over the right index, or right index becomes less than left index, in that case we are supposed to stop the recursion because they will form an invalid range in our array. So I will basically check if left index is already greater or equal to right index. I will basically say return, as it has void return type. I will return without passing back no value, and then what I am supposed to do is to partition, and partition means that I will partition my entire array. So I will call partition function, sending array reference, the address of the first element, then left index and right index. So what it will do, it will call this partition for the entire array, and it will give me this, it will give me back this index. Okay, so I have to take that index, let's say PIDX, so it's pivot, let's say pivot index, and then according to this pivot index, because pivot index is kind of plays a role of a separator here, something like the subarray which lies in the left and subarray which lies in the right should be sent to the partition again. So how? I will say quicksort, sending array, left index, and pivot index, okay, as the left side. Okay, if you remember, we included this partition index in the left side of the array, so it's going to be included. And what about the right side? It will be pivot index +1 and right index. Okay, so as you saw here, this is our pivot index. We start somewhere here. Okay, this is our right index, and this is our this is our right, and this is our left. Okay, this is left and this is right. All right, so this is it, and this will perform this like calling a quicksort and performing partition over and over until this condition is met. So let's try to check this. I will get rid of this now because we don't need it, and we will call quicksort function. Let's see. Okay. All right, seems like we have this. Okay, so this is normal. If let me add something else here, -5, I don't know, negative, no, not negative, like positive 10, one more 10. Let's see. I didn't test it before, so let's test it again. So, okay, 10, 10, all right. So this seems like it performs the quicksort operation normally well. So, okay, we can keep it. As I said before, you can start this one from left index and this one from right index, but in that case, we have some kind of something that we are supposed to consider. The first one is that we will, instead of using do while, we will use while repetition here, and then we have something else to check before we continue. It is after we swap, we have to increment the low and decrement the high indexes as well, because otherwise, imagine you have something like this. Imagine you have a situation where you, for instance, you will see this if you test it. If you have low index pointing here and right index pointing here, actually it's high. So low pointing to here and high pointing to here. So, okay, we swapped. Let's say we swapped. And when we swap 5 and 5, they are the same. And then there's a possibility that, let's say, pivot was the 5 for some subarray. I don't know which one. And in that case, in the next iteration here, it will come back and it will check array low with the pivot. So 5 is less than pivot. Let's say pivot is 5 in our case. So is 5 is like less than 5? No. Okay, it will skip this. And then is 5 greater than pivot? No. So it will skip this one as well. And then it will check high is less than low? No. And it will no, it will continue swapping. Then swap, it will swap 5 and 5. So it will keep doing this. Come on. It will keep doing this over and over, and it will turn out to be an infinite repetition. So that's why you have to do this after swap. You have to increment low and decrement high. If you change this one to left index instead of left index -1, and this one to right index, and also these two should be while instead of do while in that case. Okay, and another mistake that you might have in your code, which I usually do myself. So here, as you can see, I included pivot index in the left. Why? Because each time here, I increment and decrement at least once, and then I check, right? So that's why, even if I found that the right element is 8, I will decrement high by 1. So each time high will be 1 less than the previous pivot index. So that's why if you do not include this, let's say if you have -1 here, like -1, pivot -1 means that you didn't include this 0. And in that case, if you compile and run, you will see that some elements, for instance, you see, are not in their correct order. Or let's get back to our original array, which we saw the examples on. So as you can see, 0 is not considered in the left side. So everything here is somehow sorted, and this one is sorted. And this one was not even considered. So that's why this can be your mistake. So be careful with the indexes, the boundaries. Okay. So I think that's all what I was about to say about quicksort. And the name, as the name suggests, it's quick. Sometimes it's even, in some cases, it's even better than the merge sort that you have already seen. Many of you have already seen. So again, depending on the, of course, implementation, and depending on the case, you might choose this one or the other. It's up to you. But when you choose, make sure that you are careful with the boundaries, the indexes, and also these conditions. Because if you have something slightly different, if let's say other than like instead of strictly less than operation, you might perform less than or equal to, or here, for instance, instead of less than or equal to, you might perform strictly less than operation. In those cases, you might end up having either infinite repetition, or you might end up having some kind of incorrect result. Okay, so these are something that you should be careful with. But the rest is, as you can see, is kind of simple. We just perform basic recursive function and the repetition here and some pointers as well. Okay, so I hope you enjoyed the video. If you have questions, you can ask them later. And okay, that's it. Take care of yourself. See you in the next tutorials, and bye-bye.